Because this factor, x minus 3, is the part that's going to 0, right, when x goes to 3? We want that to cancel with something on top. And look, amazingly, it's going to. It's crazy how this works. But it does, all right? Root x plus 1. There's a certain beauty to math that I appreciate. That it's just amazing how everything just kind of works out the way you need it to work out.
With textbook problems.
With what?
Textbook problems.
Yeah, you're right. You're right. If I were to just grab a random function out of the bag of functions and ask you for a limit, chances are we couldn't do it. But that's why we have computers. And look, don't take that the wrong way. The computer, I've got like something, like a piece of grass or something stuck through my pants. Computers can do a lot of math for us, but somebody programs those computers and has to turn a bunch of binary zeros and ones and electrical signals that are either on or off into all this crazy stuff that we have now these days, right? So there's someone behind it, and you know, you actually take courses. Now there's CS majors right in here, right? So I'm not a CS major, I never was, but I can appreciate what's involved in coding. And it's a delicate subject, CS. There's a lot of issues involved. You got to know what's going on with that program, or you can cause chaos. All right, what's the numerator? X minus 3, denominator. I'm just going to leave it like it is. And we get the x minus 3 factors. See, this is an entire chunk. I can just cancel the whole thing with this. I'm going to write the limit one more time. Because I want to make sure you know what's here still. 1 on top. Bottom. Square root of x plus 1 plus 2. I don't need the parentheses around it anymore. Direct substitution, we should be in business. So we plug in 3 here.
Drop the limit and plug it in.
4 root 4, 2 plus 2, 4, 1 over 4, 1/4. That function is headed towards 1/4. As you get closer and closer to 3, that function was headed to 1/4. All right, so we have factoring, we have getting common denominators, we have conjugates, right? How do you think you get good at this? Yeah, you practice. You practice. All right, I think this will be the last one of this type. I'm going to push a little bit here. Limit x approaches 4 of, no, I want to, 1 over the square root of x plus 5 minus 1 over three over x minus 4. Yeah. Yeah, it's bad. Let's just double check because I just made this problem up. So if I plug in 4 here, I get 4 plus 5, 9, root 9, 3, 1/3 minus 1/3, 0 over the bottom, 4 minus 4, 0. So we do have a problem. So I'll give you a hint. This is not factoring. Common denominator, and we have a radical in there, don't we? Take care of the common denominator first. Put the two together. So just to illustrate what I'm going to do, I'm going to multiply the top and bottom of this one by 3. And I'm going to multiply the top and bottom of this one by root x plus 5, root x plus 5. That's how I could create the common denominator, right? Now if you want to do your cross multiply thing, whatever you want to call it, that's fine. But you should be able to put those two together. Lim, x goes to 4. Can anyone tell me what the new numerator is going to be?
X times square root.
Wait, x? Hold on. 3 minus
Numerator, sorry. 3 minus. Numerator, 3 minus.
root
Wake up.
x plus 5?
Yep.
That's your new numerator?
I was thinking denominator, wake up.
Yeah. What's below that? 3 times root x plus 5. And then the big division bar, what's under that?
X minus 4.
X minus 4. And yeah, if you want to put it over 1, go ahead. I always like to put it over 1 because I know I'm going to wind up doing something with it eventually. Maybe, I don't know. But I like the balanced look of that. It's kind of like this. If I write 12 over 4, say over 3. If I write that, what is that? It's written badly is what it is. Okay, that is not clear. You have to make one of these division bars bigger to know what's happening. Because if I do this, that means you're going to take 3/4 and reciprocate it up like this. If I do this one instead, that means you do this first and then divide through and you would get 1. So 2 different results. That's why I like to draw the big division bar, have my fraction clear, 2 clear fractions here. Now what? We're going to do the conjugate. Let's just check though real quick to see that we have not solved any of the problem. If I let x go to 4 right now, this is going to be 9, root 9, 3, 3 minus 3, 0. 0 over 9, root 9, 3. 3 times 3, 9. So I have 0 over 9 over
0.
0. So I still have 0 over 0. I haven't fixed anything, right? The only way I'm going to fix it, ever, is if I can get x minus 4 to go away. Right? If I can get this out of there.
Multiply x minus 4 over 1.
Yeah, but if you flip this and you put it up there right now, it's still on the bottom. And so you're still going to get 0 on top, 0 on the bottom. So it doesn't fix it. What I'm saying is you need x minus 4 to cancel. And I don't see any x minus 4s anywhere up here. But we have the conjugate. Right? You see a radical up there? Here comes the conjugate. And I'm going to throw it right here. There it goes. I'm going to put it right there. And what is the conjugate going to be here? Go ahead. Go for it.
Negative square root.
Just rewrite this just exactly the way it is. And change the sign between them. Good. 3 plus root x plus 5. And then here, 3 plus root x plus 5 again. See, the conjugate of 2 terms is the same thing, the same 2 terms, changing the sign between them. That's all it is. And now you have the pleasure of multiplying this out. I'm going to throw parentheses around this just to, again, stress what I'm going to be multiplying. Bringing the limit along for the ride. I shouldn't say that. The limit's driving this whole thing. It's not there for the ride. What about that multiplication across the top there? 9. Do I care about the middle ones?
No.
No. Okay, so let me put the 9 there. This next part can be a little bit complicated, so take it slow here. Here to here. What's the root times itself? The root times itself without the root, right? Is it positive or negative? Negative, right? Because it's a positive times a negative. So what you have here is minus the thing that was under the root, x plus 5. And you need that in parentheses because the minus will have to distribute to both of those. Over, now this is ugly. I have 3 times root x plus 5 times, in parentheses, 3 plus root x plus 5 again, close parentheses. All of this over x minus 4 over 1. And as bad as that looks, do you see it? Yeah. Yeah, what happens up here when you distribute that through and clean it up? You get 4 minus x? You get 4 minus x, which is almost x minus 4, but you're off by a sign, aren't you? These two, when we put all this together, that's 4 minus x. I'll just write it above here. This turns into 4 minus x up here. Yeah? 9 minus x minus 5. So my next line will be limit x approaches 4. And I'm not going to write 4 minus x. I'm going to write negative 1 times x minus 4. So we did this earlier, didn't we? When it was off by a sign. I was off by a sign. I factored out a negative 1. Over 3 root x plus 5 times, in parentheses, 3 plus root x plus 5, close parentheses, and then over x minus 4, over 1, right? Not for me, though. I'm flipping that up on this line. We still good? They go away. They cancel? And that's what we wanted. We wanted that to happen at some point. And it finally did. If you're not getting that canceling to happen at some point, then something in the algebra is off. And there's a lot of places to be off, right? All right, I'm going to write my limit one more time. There it is. What is still on top here?
Negative 1.
Negative 1. On the bottom is this really ugly expression, but I want to make sure I write it down correctly. The parentheses here, 3 plus root x plus 5. Bam, there we go. Now we should be able to direct substitute. And the reason why we shouldn't worry about it being 0 over 0 is because we eliminated the part that was turning into 0. But please do be careful here. Make sure at this point you plug it in properly. I'm going to have negative 1 over, no more limit, right? No more limit. 3 times, what's this here? 9. Root 9 is 3. So 3 times 3, I'm going to just write that down. 3 times 3, parentheses, 3 plus 3. So this is equal to negative 1 over 9 times 6.
That will be 15.
That's 9 plus 6. 54.
Oh,
Negative 1/54. See, it's just algebra on steroids. How much of this was calculus? I mean, honestly, how much of this is calculus? Writing the limit in the front, right, the whole time? That's really, I mean, honestly, I told you that. Right now, the concepts are not way out there, I don't think, because all you're doing is just plugging in 4 at the end. The only thing I guess you could think is calculus is, in the beginning, you get 0 to 0, and so that tells you have to do a bunch of algebra, and then it's a bunch of algebra until you get to the end, you plug it in. It's the algebra. And that's why I always say that in Cal 1, it's algebra on steroids. You're really going to get tested on how good your algebra is. All right, I have about, I don't know, what, 45 minutes left? We're not going to stay late today? All right, there were two important limits that I said that you need to know. And there they are. Now you could actually determine what those are, all right? You could verify that the first one is 1 and the second one is 0 by looking at the graphs. All right? If I graph sine x over x, we would be able to see what it does. And we'd be able to convince ourselves that as you approach 0, it comes up to 1. And if you graph this one, you would see the same thing. But I just want you to try direct substitution. If x goes to 0, sine of 0 is 0, the bottom is 0, you get a bad situation, don't you? Same with this one. Cosine of 0 is 1. Good. Minus 1 is 0 over 0. So you get a bad situation there. How could you do some algebra to this to eventually get 1? Or how could you do some algebra to this to eventually get 0? And my answer is you wouldn't be able to, okay? It is very difficult to show that this limit is 1 algebraically. It can be done, and there's a really awesome proof of how to do it, but I don't have time in this class to show you, so if you're interested in it, I don't mind you coming by my office and I'll show you. It uses this concept of almost what's called like a squeeze theorem. Anyway, okay. We won't talk about it. Okay? But if you're interested, I can show it to you. You need to know these two. Hardwired. All right? Especially this first one. You just need to know it. That's 1. Now I need to adapt this just a little bit. Okay? I'm going to just add something to this. I don't want you to think of that formula the way it appears here. This is the way it appears in a book. Here's the way I want you to look at it. If you have a limit, all right, and you have something, I'm not even going to tell you what it is. Could be x, could be a different letter, t, it could be w, and it's approaching something else. Like it could be x is approaching 2, or it could be y is approaching 5, or t is approaching -1, or z is approaching pi. It does not matter what is going on in the limit, all right? It doesn't matter. And you have sine. And inside sine, you've got some junk. Now, when I say junk, I don't mean like the word junk. I mean just something is in there, right? It might be sine x. It might be sine of 5x. It might be sine of x squared plus 1. It's just some expression in here. I'm going to call it junk. And you're dividing that by the exact same junk. And it has to be exactly what you see there. The junk here is the junk here. Then the answer to this limit will be 1 as long as these two things are true. If 1 junk equals junk. What do I mean? These two junks are the same, okay? These have to be identical for this to work. So if you have 2x right here and you have 5x right here, this doesn't work. They have to be perfect, exact, identical copies of each other. And the second thing is that junk must be going to 0. This arrow is meaning like in a limit, this junk is going to 0. So let's go back and look at the formula that I've told you need to know. I have a limit, I have something approaching something, right? Do I have sine of some junk over some junk? Do these two junks match? Is that junk going to 0? Yes, because x is going to 0, that's going to 0. The answer is 1.
So junk must appear 3 times.
No.
Just twice.
Just twice. Let me give you a different one, just so you can see it, all right? How about this? What is the limit as x approaches 1 of sine of x squared minus 1 over x squared minus 1? What is this limit? It should be 1. Now let's see why. Do I have a limit of something going to something? Yes. Do I have sine of some junk over some junk?
Yeah.
These two junks match? Are these two junks going to 0? As x goes to 1, 1 squared minus 1 goes to 0. See what I was saying? It doesn't have to appear over here. What matters is whether or not that's going to 0 and that's going to 0. The answer to this would be 1. Got it? Let me show you something that wouldn't work, just so you can kind of see like some danger spots here.
So it must equal that.
Must equal what?
That. Technically.
No. Because look, let me give you this example. Just change that one up just a little bit. Sine of x minus 1 over x squared minus 1. So
for example, you weren't approaching 1, say you were approaching 3, then it wouldn't equal 1.
if this was approaching 3,
No, this one.
this one was approaching 3 here,
The one on this side.
over here. If this was approaching 3, then you would have 3 minus 1 is 2. Sine of 2, well, that's something, right? And then down here you would have 3 minus 1, which would be, or 3 squared minus 1, which would be 8. So you get sine of 2 over 8. That's a number. There's no problem there. That's not even a calculus problem. So that wouldn't matter. So is this answer 1? It is not. You have a limit, right? You have sine of some junk over, those junks don't match. They don't match. So you cannot use it. Now, are they both going to 0? Look, if this goes to 0, doesn't it? This goes to 0. That does not mean this thing goes to 1. They have to match exactly. Right? Okay. I'm going to continue that problem because we can actually solve it. That'll be our first good introduction. So I'm going to continue this. So I'm sitting here, I'm like, well, maybe I can figure it out still. What would I really, really have liked to have down here instead of this? Just x minus 1, right? It would be really nice if that was x minus 1, but it kind of is. Because I can look at x squared minus 1 as what? Difference of squares. I could write it x minus 1 times x plus 1. Doesn't matter which way, right? I could do that. Just so happens that this factors. That's good. Now, carefully watch what I do. This is not calculus. This is just algebra. There. All I've done is just peeled it apart. We know that when you multiply two fractions together, you multiply straight across, don't you? So 1 times this would be this, and then this times this would be this. All I did was peeled it apart, yeah? Now, the reason why I did that is because the limit laws tell us that if you have a limit of two things being multiplied, you can do the limit of each one. That's one of the limit laws. I won't bring it up. You can go back and look in your notes. So can you look at this right now and tell me what the limit of that is as x goes to 1? That's 1, right? That's 1. Because I have sine of junk over junk, they match, exactly match, and they go to 0. So I know that when I take the limit, and I'm about to do it, so I'm not going to write it again, I know this goes to 1 times, now what's the limit of this as x goes to 1? That's just direct substitution, 1 over 2. What is 1 times a half? A half. The answer is 1/2. That's what that one goes to. Yes?
You're not going to write the sign?
What sign?
With sign 1 times 1/2?
No, this right here goes to 1. The whole thing goes to 1 using that sine junk over junk idea.
Does that only work for sine?
That only works for sine junk over junk. Yep, cosine junk over junk, there's no. Nope. You with me? All right, I'm going to add one more thing to this. It actually turns out that if you do limit, something goes to something, doesn't matter, and you do junk over sine junk, you still get 1. So if they flip, if the numerator and denominator flip places in that formula, you still get 1 as long as what? The junks match and they both go to 0. That's nice. You can flip it. It doesn't matter which is which. So that's it. I'm not going to have time to get to the cosine one, okay? But everyone, deep breath. We have 7 minutes. This problem that I'm put up here always causes students issues. Let's see how you do with it, all right? But it's definitely a problem I like to put on tests. Because if you understand this, then you get it, all right? So here we go. What is the limit as x approaches 0? You want to stick with x? We've been sticking just with x. The book switches it up. They use different variables. Are y'all going to be able to handle that? You're okay with that? J? Well, they probably use like theta. Let me do theta, okay? Just so you have some variation. Theta, okay? It's just, hey, it may as well be an x, okay? But the reason why I'm doing it is because I'm going to use trig functions. So I want, theta kind of goes hand in hand. So I want to know what the limit sine 3 theta over tangent of 5 theta.
I think I know this.
You think you know what?
There it is.
Let's first do direct substitution. Let's just try real quick to see what happens when we plug in theta. If I plug theta in, theta is going to 0, right? 3 times 0, 0. Sine of 0, 0. 0. Over 5 times 0, 0. Tangent of 0. I don't hear a lot of confidence here. It's 0. Okay, look, you've got to understand what your trig functions are doing at these common angles like 0. All right? That's your sine function, right? At 0, 0. Your tangent function looks like this thing, and it has asymptotes. Where are those asymptotes? Close? Nope. Negative pi over 2 and positive pi over 2. All right. It's getting shaky in here. All right, let's continue. Let's continue. I have 0 of 0. I need to do some sort of algebra, some sort of trick. But I've got that sine junk thing, right? I've got that sine junk thing. So here's the way I approach this problem. I first start by peeling everything apart. I'm doing it this way just to take my time, since this is the first problem I'm doing. Later on, it may not show as many steps. You agree with that? I'm just peeling this thing apart. Now, 1 over tangent is the same as cotangent, which is cosine over sine, isn't it? So I'm going to go, again, limit theta goes to 0, sine 3 theta over 1 times, you said it was cosine over sine, so cosine what? 5 theta over sine 5 theta. And while I'm here, let me just ask you real quick. Can I pull the 3 out? And can I pull like the 5? Could I have just pulled the 3 and the 5 out to begin with? No. No. That's like you get whipped for that sort of thing. I mean, there's like, little mistakes and there's big mistakes. And you can never mess with the argument of a trig function like that. You cannot just go in there and start pulling numbers out. This is not multiplication, right? The argument is trapped by the trig function. Right, I'm going to continue. I'm going to do, again, I'm going to rewrite this. And because of time, I'm going to cheat. I'm just going to take that sine right there, sine 5 theta, and I'm going to just move it over. And so do you see that what I've really done is just peeled this thing completely apart, ripped it apart into all of its different components, right? It's got your sine 3 theta, a cosine 5 theta, and a 1 over sine 5 theta. I would like for someone to tell me which of those three factors is causing the biggest problem. Which one? Which one? The 1 over sine 5 theta, right? Because that's causing you the division by 0. Do you agree? Like this right here doesn't have a 0 down here. This doesn't have a 0 down here. This one does. I really have to deal with the fact that this is causing division by 0. What would I love to have seen up here that would have made this thing nice? A what up here? Not sine 5 theta, 5 theta, right? If just 5 theta was up here, then what would this limit on this one be? It would be 1, right? Everyone understand that? Using that junk thing. If that was a 5 theta, I would be happy.
Do we have to multiply by all of them now, or just that?
All of these are multiplied, so remember when you multiply something, multiplication doesn't distribute over multiplication. Like if I have x times y times z, and I say, hey, multiply that by 3, you don't go 3 through to each one, right? It's just 3 in front of them, right? These are the little subtle things that we want to make sure we know, you know? It's a great question because I guarantee you're not the only one who wants to do that. Do it on every one of them. Okay, so here's what I'm going to do. Here it comes, 5 theta. I'm going to introduce it. But what I do to the top, I must do to the bottom, right? I can't just throw 5 theta in there. I can throw 5 theta over 5 theta. Yes? That's fair? That's legal?
Yeah.
Okay. And because, again, I'm almost out of time, on the next line what I would do is I would slide that 5 theta on top over this one, and that would leave me with a 1 here. Understand? Now, is this the problem? No. Is this the problem? No. Is this the problem? Not anymore. What is this limit going to go to? 1. Oh, shit. I created a new problem, didn't I? Didn't I create a new problem?
Yes, sir.
I have division by 0 still now. But I'm clever. And I see a sine 3 theta over here, which was perfectly happy and wasn't causing any problems. But this theta that's causing an issue here, I can actually use it by taking just the theta and sliding it under here, like this. Got it? You're going to have to go back and watch this video. Normally I'd write this line by line, but I'm out of time. So now I'm here, right? Now I'm here? Why did I do that? Why did I do that?
I'm so lost.
Okay. Wasn't this 1 over 5 theta causing division by 0? I don't want that. That theta was now a pain in my ass that I had to get rid of, right? But I'm going to use the fact that if this was 3 theta, I wouldn't have a problem, right? And here was the theta that was causing me an issue. I'm going to use that here, and I'm going to introduce a 3 over 3 out here. Is it because what? That one, this hurts, huh? I think everyone, is anybody on board? You think one?
Shot me out of a cannon and into.
No, we'll just have to, I think we'll have to start next class with one of these. Yeah.
So basically, you use like 1 over 5 times theta.
This right here, 1 over 5 times 1 over theta? Uh-huh.
If you did that, it would be 1 over 5 theta.
That's right. I moved it over. Yeah, I mean, we'll talk about it next class. Look, do your homework for 1-4, but I'm going to, in the videos, there are homework problems that go over this. So you just might want to get to that and give it a shot. All right. Let me see. No, I don't pick up homework. I don't ever pick up homework. I might check it. Do it, bring it. Do it, bring it every time. Hey, I offered my other Cal 1 class bonus, and I wanted to offer everyone here the same bonus. If you come by to my office for help, Okay, I will keep track of that, and so I will reward you for coming in for help. I know some people can't. So if you form any sort of study group outside of class with your other classmates, and you all meet on a regular basis, you know, once every week, once every 2 weeks, and you can prove to me somehow that you are meeting with the group in this class, I will keep track of that, and when you're asking for bonus at some point, I will be like, okay, I'm okay with giving you something. All right? But you're not going to get bonus just for showing up. Huh?
That's all.
Yeah, if you, as long as you, yeah, well, yeah, but what I'm looking for is group, for you to like pair up with someone. Yeah, uh-huh. But you also have a camera. You could like take a picture of the group. I mean, there's technology. It's easy. Hey, hey, we came to study today. Look.
Everyone, let's just show up the fireworks.
Get a costume.
Let me turn my camera off real quick.